Hey guys, thanks for tuning in. Today we are installing the new E3D Hemera, formerly known as Hermes, on the CR-10 V2. To do this install, we're obviously going to need a bunch of different things that you see in front of you here. First, we're going to need the Hemera from E3D. It's a 24 volt Hemera that we need. This is a 24 volt system, not like the 12 volt systems of the original CR-10. We're going to need a bracket to adapt this to the X carriage here, which I've designed up here. It's kind of like a prototype, so we'll see how this goes. And the other part of the bracket bolts onto the Hemera itself. So this bracket on there, this one on the X, and then the two of them made up like that. We need a way to attach the BL Touch. So in our case, we're BL touching this. The fan will bolt onto the stepper motor here using the T-slots. And then it has a provision for the mount like that for the BL Touch, and it's adjustable. In this case, it comes with a 50-15 fan. And the 40-20 fan actually has the spacing between the bolt holes on it that line up perfectly with the T-slots on the motor. So we're going to switch to a 40-20. So on the topic of the fan, we happen to be using this mount. You don't have to use this one. There are many out there. Any of them that bolt onto the motor like this one does will work because you're bolting onto the Hemera. It's not specific to the printer that you're installing it on, or specific to even the mounting plate that you're using because it's not bolting to that at all. So some of them will actually have the fan shroud component built right into the mount itself. In our case, we're just going to print out a separate fan shroud that will glue into the opening of the motor that's attached onto here. We have the original Ant Clabs BL Touch, and we have the extension cable kit for the BL Touch. We've got some solder. Since we are cutting the leads for the fan, we're going to be soldering on the new ones. We're going to reuse the heater cartridge in here. We're going to swap the thermistor definitely because they use the cartridge style instead of the bead. So we'll need to solder the thermistor as well. And then you want a lighter or heat gun or something to heat shrink your solder joints. So with that said, let's start unpacking the kit and see what's included. All right, let's open this guy up. There we go. Lift here. Shouldn't need instructions for this, but it's kind of fun anyway. So right off the bat, you see the meat and potatoes of the unit. So you've got the heatsink, which now directs the air up instead of into your face like the Titan Aero did, drying out your eyes in the process. We have these nice T-slots that are built in. The ones that are on the side of the heatsink, they're not accessible because the heatsink's bolted on there. So they have these little square nuts pre-installed in there, and likewise on the back side. So these little T-slots, they don't take your standard hexagon style nut. They have to be square and they have to be 2 millimeters thick or thinner. So the first set that I bought was 2.2 millimeters and they don't even slide in the slots. So we'll link down below to a random Amazon listing that I happen to use to find the nuts that will fit this. And I'm going to use those same nuts to slide into slots that I've designed in the mounting bracket. So as I said, the fan is going to bolt right onto the front of the unit like that. The fan will attach on here, obviously. The beefy lever arm right here, tension adjustment for the tension against the filament that this arm is placing. On the bottom, we're going to screw in the heatsink into there, and obviously motor cable onto here. With just a couple screws, you can remove the whole heatsink, which will have the dual drive gears, Bondtech style dual drive gears in there. And I believe that's all hardened tool steel, so you don't have to worry about abrasives wearing out the drive gears themselves. So there's that. Open here, press and lift. Let's just brutalize the packaging. There we go. So there's the fan for the side of the heatsink. We've got the standard, if you've seen any of the other videos we've done on, say, Titan Aero, you get the same kind of accessories. So we have a heater cartridge, and I think these ones are actually lower wattage. Yeah, these are 30 watt heater cartridges. We've got that. An extension cable with the Molex Microfit 3.0 on the end. Their cartridge style thermistor that we're all familiar with the Molex connector on the end as well. There's the fan. And then you've got a silicone sock with a V6 heater block and a 0.4mm nozzle. And inside here, there's also the new heat break. So the heat break is different than the heat break from the previous series, any of the V6 stuff or the Titan Aero, using the same components really. So it's much thinner. So this top part was an M7 thread on the previous ones. This is way tinier, obviously. So that screws up into the bottom of this guy here. And I always love having silicone socks on all of mine. Even if it is copper plated or nickel plated copper, I still put a sock on it. We've got some thermal paste. So this is to increase the heat transfer from the cold side here into the heatsink. You don't put it on the hot side of the threads. And then, as I said, the little 0.4mm nozzle. We've got an extension cable for the stepper motor. And then just the fixings. So you've got all the little grub screws. There are 4 of those square nuts that I was referring to, but it's just not enough for the whole install we're going to do. And there's a selection of M3 screws as well. A small piece of PTFE tubing. So you're probably wondering, I thought it was all metal. It is. The PTFE is just to go in here to guide the filament into there. In some cases, depending on your setup, you may actually have PTFE just to guide the filament all the way to the hot end. It's not actually Bowden anymore, but it's just to kind of keep the filament constrained to a specific path. So that's what we'll use this for anyway. And then a single zip tie, but we'll probably need a couple more to do some wire management with the BL Touch cables. Okay, first, I'm just gonna start unbolting stuff from here. So this whole assembly here bolts through the back of the X carriage. So let's turn this guy around. There are 3 M3 screws in the back, 1 on the top and 2 on the bottom on either side of the wheel. And then this assembly just completely comes off. So as I mentioned, just to make my life easier, there's no point in changing the heater cartridge. I don't think there's anything wrong with this one. So I'm gonna reuse that, but I will be cutting the 2 white wires, which are for the thermistor, and I'll be soldering on the E3D one. They don't have any polarity, doesn't matter which one's connected to which. Unlike the fan, we obviously have a negative and a positive, negative being black. So it matters how those are connected. And then these 2 leads here are for the cold side of the hot end, so that will be the cooling fan that connects, that attaches to the heatsink, and so they also have a polarity as well. So we need to take the rest of this apart. So in the back here, there are 3 more M3 screws. We're going to need to unbolt them. So I've got the 3 out of the back, and I'm also going to have to remove the 2 on the fans since they're screwed into either side of this kind of clamshell. So I've got the fan now removed from this side, and on the other side, we have the 4 bolts on this fan. There we go. So there we have the heatsink portion of the hot end. Looks a lot like a E3D V6 kind of design. Okay, gotta be careful we don't want to damage any of these wires. There we go. Okay. And so the thermistor here is that pinch style thermistor. We're not using that, and it is a Phillips screw instead of Allen bolt of sorts. So I'll have to grab a Phillips screwdriver as well. And then the heatsink, the heater cartridge is held into the heater block with this little grub screw. All right, now with a Phillips screwdriver, or star if you're one of those, unbolt the thermistor, and because I'm not reusing it, I guess I really didn't have to unbolt it, but I'm just gonna pull it out of the heater block there. It's just a little bead, and there's like a thermal kind of paste of sorts in there, white paste. And then with a really tiny Allen key, we should be able to remove, or at least loosen, this grub screw. And since this is a brand new printer, we have no problem sliding this out. If your printer has seen some hours of use, this may be a lot more difficult for you to get out. Luckily, you can kind of force it out through the other side. Okay, so we are done with the hot end, and actually we're done with the Bowden tube entirely. We're not going to use this anymore. There we go. Don't need anything on there. Put that aside. So I'm just going to separate the wires. They've got this Kapton tape, kind of bundling them all together. And so just above the heat shrink, I'm just going to cut that off. Okay, so we'll reuse that later. And we're going to use the provided fan for the heatsink cooling, so we don't need this one. So the way that I've designed this bracket that attaches to the carriage here is these bolts that go right through the V-wheels, the heads of them are going to be recessed into the bracket so that they sit flush, the bracket being like this, and then they'll bolt straight through, and there should still be enough length on them that we don't need longer bolts. Before I unbolt these, I want to reduce the tension on the bottom wheel here by loosening the eccentric nut. So I'm going to need this guy. Just turn it this way. There we go. This way. This way. There. So now, there's no tension on that. And then just unbolt them. So just before I fully take this one off, on the back we've got the nylock nut, then there's the V-wheel, and then there's an aluminum spacer. So just kind of take note of that to make sure that we put it back together in the same fashion. The bottom one, because it has the eccentric nut, that takes place of the aluminum spacer. So there's the eccentric nut, and the little bulgy part there, the eccentric hole, goes through the back plate there. So just make sure that you're assembling it that way again. And now the only thing holding this on is the belt. You could have removed the belt before you started unbolting everything if you wanted to. You may want to reduce the tension on your X tensioner, which is on the right-hand side if you're facing the front of the printer. Loosen the 2 bolts on that and release the tension on the belt to make that easier. We're gonna definitely have to do that before we put the belt back on here. So as I was kind of describing, this is going to go like that, and then we're going to bolt through here, without the washers. There we go. So the tolerance on this wasn't quite large enough to fit the washer. We don't really need the washer, but now they sit completely flush, and then the other part will bolt onto here later. So I'm going to do the top 2 first, I think. So just put it back together in the opposite order. Perfect, so those are now bolted on. We had enough length in the bolts, as I had hoped, that we didn't need to replace them with longer ones. And then the bottom bolt, remember this is the one that had the eccentric nut. Make sure that the bulged out portion of the eccentric nut goes into the aluminum plate, into the hole there. And then you're not going to be able to just slide this wheel on like we did the other ones. So feed the bolt back in, and then you should be able to line it up and then feed the bolt back through. So now we can reattach the belt, and as I had mentioned, we're probably going to need to reduce the tension on the X-axis tensioner, unless we're really lucky here, because it should be a pretty tight fit. Yeah, I got it in. Okay. So you just slide the belt through these slits in these fingers and make sure that the belt is centered, so it should be running in line with the groove in this extrusion here. So I think we're done at the back of the printer. Let's turn it around. So there's the plate, and these holes here are where we're going to bolt the other portion of the plate that is going to be attached to the Hemera. To bolt through here, I've got slits in the top and in the bottom to put nuts behind there so we have something to thread the bolts into. These are the little square nuts that I was referring to that we purchased in addition to the ones that came with the kit. And we're going to slide these through those slots so that we have something to thread those bolts into, as opposed to the standard 6-sided hexagonal nuts that you'd normally use. And they should, in the top, just kind of drop in there, and then we can bolt in. And then there's 2 in the bottom here that we'll have to hold with our finger while we screw into them. The holes themselves could have been made a little bit smaller, and then we would like friction fit them or even heat them up and melt them in. But in this case, they just slide in loosely. So at this point, we may as well bolt the other plate to the back of the Hemera. So the Hemera is going to essentially bolt on like this, more or less, with this other plate. And so the nozzle will be over at this side. This plate is going to bolt this way. With those recessed holes are for the heads of the bolts that are going to go in there. They're M3 bolts. I believe there's 6mm bolts that we need. And if we're lucky and kept all the hardware that we just took off, we should be able to reuse some of them. But I have a large selection of M3 bolts that we can use. And this particular plate is directional in the sense that the 2 holes here where it bolts on are close together and these ones are further apart. So this would actually go like that. Okay? So keeping that like that, it's going to bolt onto the Hemera like that. The Hemera only has nuts in the 2 T-slots, so we need to add 2 nuts that came with the kit to the other 2 T-slots here. So the ideal length of screw is a 5mm M3 screw, and we are using button head screws instead of like socket cap. The socket cap tend to stick out further, and these recessed holes only have a deep enough well in them for the button head screws. And I'm just pre-threading them because the holes are kind of tight. There we go. And then again, make sure I'm putting that on the right way. You should be able to just screw down into those square nuts that are in those T-slots. And you can just double check your assembly because there is a little bit of play in those nuts in the slots, and just see that it's aligned properly, that's not skewed in comparison to the end of the motor there. I've already installed one of the square nuts in this slot here. I'll just drop one more down into this one. Press it in if need be, and just double check that it lines up with the hole. There we go. And then with any luck, I'll just need 2 more M3 screws. These ones, it doesn't matter if you're using socket cap or anything, as long as they're not too long and that they don't hit the back aluminum plate there. We've got 2, they look like 8mm long M3s from the disassembly of the stock hot end and shroud that we can use for these. So there are 2 more M3 socket cap screws that are part of the E3D kit that we won't need for other things, but we're going to use them for the 2 screws at the bottom here, the equivalent of these, but down at the bottom. They're long enough, but not too long that they go through and hit the back plate. And we'll need 2 more square nuts. Now this one's a little bit trickier because we don't have gravity helping us with the nuts. So I'm going to use tweezers, or in this case, the little flush cutters, to hold that while I thread in these screws in those holes. And that's one really nice thing about the Hemera platform, if you want to call it that, is unlike some others where you have this mount that needs to stick out from the X carriage, you end up having that cantilevering action. And the more that it sticks out, the more likelihood there is for things to kind of flex or have some movement to them. This may as well be like welded onto this carriage. It's all of 6mm or so away, so you don't have that cantilevering effect. And being that they're just kind of flat plates that it's mounted to, there's going to be 0 flex in these whatsoever. Before we go much further, I want to use up some of the smaller pieces that are here before I lose them. So we'll start assembling the rest of the hot end. I've got the heat brake, and it just screws in the bottom of here, but as I mentioned, we need to put thermal paste on it. This little white packet here has a tear in it, and you only need a tiny bit because we don't want it to really ooze out everywhere when we thread this in. Just kind of brush it on. Just like that. That's probably more than enough, and it will make its way down the rest of the threads. Okay, just finger tight for now. Now we have the heater block. A couple pieces we'll pre-install here. We have these tiny grub screws. This is the same type of grub screw that we had to loosen to remove the heater cartridge from the stock heater block. So there's going to be a couple of them actually. One grub screw goes over here. This is the smaller hole, is for the thermistor. And then on the opposite side, we're going to have a longer screw to pinch the heater cartridge. So that's one of these black ones. So they're just in there so that they don't get lost. They're not tightened or anything. So you want both of them to be on the bottom so that you can access them if need be. And then this threads onto here. And don't thread it all the way up because it doesn't go all the way. You should still be able to see a couple of the threads on that heat brake. And then we'll thread in the nozzle. And the nozzle will make contact with that heat brake and stiffen the whole assembly up. So everybody kind of has their own preference as to how they want their heater block oriented for various reasons. The key thing is to make sure that there's a tiny gap here between the top of the square portion of the nozzle and the heater block. The idea is that you don't want that nozzle tight against the heater block. You want it tight against the heat brake inside the heater block. So I've seen too often where this will be, say, unscrewed like that, and the nozzle is completely tight against the heater block, but there's no tension there at all, right? So it's a balancing act of choosing the orientation you want, but also making sure that your nozzle is tight against the heat brake and not the heater block. So we could orient it like that, and we have a couple sheets of paper worth of gap there. Or if the more we unrotate this, the more that the nozzle needs to go in, and the tighter that we make this, the more the nozzle sticks out, right? So now we've got maybe 0.5 millimeter or something of clearance there. So it all just depends on how you plan on routing your cabling. We have a gap back here between the back bracket plate and the side of the Hemera. So we could actually feed all of our wiring up the back for a nice clean installation instead of seeing a bunch of it come up the front. That's what I'm going to do. So I would probably we might not have enough clearance there. It might be a sharp bend. I might want it that way. I mean, we'll just kind of play with it and see how it goes. But the idea is that I'm going to run the wiring up the back. So earlier I cut off the cooling fan right here. I left the part cooling fan, which we are going to also replace, but I left it so that you don't confuse which set of wires is which. I know that this is part cooling fan because it's still there. And then obviously the thermistor is different color entirely. Before I go attaching any of this here, I think we should terminate the rest of the connections. So I'm going to strip with my cutters, separate the two wires for the thermistor. And then strip them. We may as well strip the rest of them while we're at it. So the thermistor, you could solder it directly onto those. I don't like working with these wires. A combination of the braiding that's on them gets in the way. The wires tend to be pretty thin, and Molex connectors are really nice. So I'm gonna actually use the Molex connector that they gave you for this purpose so that it can be kind of quick connect like that. And we're gonna solder these onto those leads. We're definitely not going to need all that slack that they gave us. And even as it is, this is quite a bit of slack because we're going to have all of this coming way up here. So we may actually want to trim the thermistor wires back further, or we'll have this big bunch of wires we'll have to deal with. I'm going to cut these zip ties that are holding the nylon braided sleeving on here and pry back the sleeve. So I've actually reconsidered. I am going to attach the heater cartridge into the heat block there, just so I can gauge how much I need to cut back the thermistor wires. You can't add wire back. Well, I mean you can, but it's not nice and clean. So I am gonna have the block facing like that with the wires all leading out the back. I'm gonna leave it kind of slack. I don't have the nozzle tight, just so that I can easily access the holes there for the heater cartridge and the thermistor. And then on the thermistor, tighten the grub screw. And now you don't want to go crazy. You're just tightening it enough that it's not going to slide out. You don't want to completely crush it or anything. And then the heater cartridge, orient the wires, bending upwards like they are, and then tighten that black screw until it's kind of squished in the heater block. Now during all of this, it's important to note, and I should have noted it earlier, you don't want to be putting any pressure sideways against that, the heat break. It is very thin walled, it's a fragile piece. Just like when we're tightening a nozzle, you always hold the heater block with a set of pliers so that you're not putting tension against that or pressure against that, especially sideways. You can snap them pretty easily. So I slightly changed the orientation of the heater block. It's still longitudinal like this, but I moved the heater cartridge to that side. That gave me enough slack on the little pigtail for the thermistor that it nests right behind the Hemera and rests on top, which is like perfect. So I've got everything routed up here, and we're using the length of cable for the heater cartridge as a reference point for how short or long we need to cut this pigtail. So I'm just going to kind of line the two of them up, leave a little bit of extra slack, and cut this guy. There. That's better. And so now we'll just strip them and solder them together. So I've got the soldering iron heating up. While that's heating up, there's some other things that I can do. We are going to solder these, I promise. But we can attach the cooling fan for the heatsink. So again, they gave us a very generous amount of wiring that leads to the fan here. We're not going to need it. We're definitely just going to hardwire this one. I'll leave just a little bit, more than enough. And then we're going to take these pointed self-tapping screws here, and they go into these two standoffs that are opposite of the two screws that hold this entire heatsink assembly onto the motor that we used earlier when we dismantled the whole thing. Doesn't really matter how you line it up. And the fan, the sticker goes facing inwards. The way I remember that, there's this little kind of grill here to protect your fingers. Well, there you have no grill. You will hit your fingers on the fan. And I've done it. That's how I remember it. So throw these in. And they, of course, are using Phillips as well. So I'm glad I have that Phillips screwdriver from earlier. And I'm just lining up the wire with the bottom corner so that I can feed it up the back with the rest. So all the wires route nicely behind there. I'm just gonna pull this little pigtail piece off of the thermistor to make soldering it a little bit easier. All right, so I've got everything soldered and heat shrinked up here. Everything's generally the same length, so they can nicely bundle in the in the braided sleeve that I've got taped back there. And as I mentioned earlier, the hole pattern for the 4020 that we're going to use lines up with these slots here. I don't have the nuts in there right now, but otherwise this wouldn't line up. And that's fine. You could have a bracket plate that actually adapts the holes so that they do line up. Maybe this one bolts into there and the other one just bolts into the bracket plate. That would be okay. But in our case, we're just going to flip it to a 4020. 4020 actually has more volume anyway. If you multiply the two numbers, that tells you the volume. So that would be 800 cubic millimeters of volume versus 750 for a 5015. So it's a minor upgrade, I guess. Volume is not everything, obviously. You got to look at the spec sheet to see the CFM and CFM under static pressure that it moves. So I'm going to cut this fan off, and I'll leave a little bit of wire there so I can use it for something else. And then this comes with a long cable. Thankfully, due to the magic of film, we had some time to reprint the fan mount here. I wasn't entirely happy with the one I was going to reuse from another setup, so I designed this one from scratch. So this will still bolt on there just like the other one did, and the BL Touch mount portion is on the side here at a 90 degree, and it's positioned so that it doesn't interfere with any of the exhaust airflow on the side. This way, we have the BL Touch kind of inline and a lot closer to the nozzle, and we'll be able to probe all the different areas of the bed. If we have the mount over here for the BL Touch, then we're not going to be able to get all the way to the left side of the bed. It will extrapolate that probing mesh out for us to the bed extensions there, but personally, I liked having it as close to the nozzle. So we're going to use that instead, a little bit of a change there. And then the fan shroud that we've settled on is this one. This was designed by Joe Cascia. And I pulled this one off of the Sidewinder X1 Thingiverse page. We'll link to that down below. Again, it doesn't matter that it was designed for a Sidewinder X1 because it's actually really just designed for the Hermes, in this case for a V6, which is what we have here. And there's a longer one that's extended for the Volcano, which would stick down a little bit further. So that's one of the nice things, as I mentioned before, we can kind of interchange any of the parts for the most part, except for the mounting plate, for anything that mounts on the Hermes. So, I'm going to mount the fan before I solder them to figure out what length of wire I need to leave. So we're going to insert 2 more of these square nuts into the end of the Hermes there. And we will also need 1 more of those for the back of the BL Touch. So the BL Touch goes on here. This bolts on there and it gives us some adjustability so we can move it up and down, and we should be able to actually extend it down far enough to accommodate a Volcano without needing a different mount. On the back though, there's a spot for like a captive nut. So we can take one of these nuts, and we may even need to heat it up with a torch or a soldering iron and melt it in there, or use a pair of pliers to pinch it in. It's designed to be friction fit, specifically for these square nuts that we're using, because some of them are different depth and slightly different dimensions. So I'm just going to pull that out for now. And then depending on the 4020 fan you're using, you're going to need appropriately long M3 screws or bolts to reach through here, through the back plate, and then into the nut there. Before we bolt the fan and this adapter onto the Hermes there, we're going to have to insert that nut. So we'll do that now. So now that's in there, nice and flush. Take the fan, and then our 18mm M3s. So with the fan now mounted, I've just routed the cables up behind the bracket. You could have done this before you bolted on the bracket. You would have to do it before, once you have an end on here, but since I don't, I've just fed them up there, and it'll make it easy for wire management. I'll tie them to the cable for the stepper motor there. And now I can determine how much length I need, and I'll cut them and solder them. All right, so I've got the fan soldered up. Just as a point of reference, the blue wire on this Creality fan is the negative yellow is positive, so that's how those worked out. You can always test by turning on the cooling fan and touching them, and it'll only work one way. And then, as I said, I routed them up through the back. So now I'm going to attach the cooling fan. And I just kind of dry fit it and realized real quick that with the heat block sideways, the cooling fan is going to contact the heat block, at least in the orientation that I had it. If I rotated it 180 degrees, it would have cleared just fine. But then the nozzle would be pressing up against the heat block and not contacting the heat break like I talked about before. So I've compromised and rejigged things a little bit. Now it's in this orientation, forward and back, and everything's coming out this side and still routing up the back like that. And then this has a proper amount of clearance and isn't going to contact the bed or anything either. So that is just glued on. So I'm going to use Crazy Glue, CA glue. In this case, I'm using miter bond. This is the cheapest way to acquire this much Crazy Glue. And it comes with a cool activator. So this activator, the moment you spray this on, it's hardened. There's no set time. Crazy Glue normally hardens pretty quickly anyway, but especially when you're working with one set of hands in an awkward position trying to hold something on, I like to just make quick work of that. So along the rim of this, I'm just going to put a liberal amount of Crazy Glue. Okay. And then there's a little ridge that sits right inside the fan like that, and kind of tack it on. It's almost like tack welding. It will tend to discolor PLA a little bit. Turns it kind of like a white or almost milky shade. There we go. I'll give it just one more spray around here. You don't need much, just enough to kind of make it wet. And now that's on there. I definitely wouldn't be putting any force on it for now. Let it completely cure, but that's not going anywhere. So now we can mount the BL Touch. So this little slider piece allows us that adjustability into that captive nut that we installed in that bracket. So we'll install the BL Touch onto here using the hardware that came with the BL Touch in this little foam compartment. So the BL Touch comes with some bolts and washers, like little screws, not really bolts, and these little springs. So these springs are to allow you some adjustability, but because we have a slotting bracket, we're not going to need those. It's just going to be rigidly attached. So it's going to attach like this, and then the wiring is going to just run up the side here and then join in with the fan's wires, and we'll zip tie that out of the way. The mount also has a hole in the center to allow you to access that little adjustment screw. So using any hardware, whether it's the stuff that comes with the BL Touch or something else, and some more nuts, just attach the two of these together. So at this point, we're ready to attach this bracket to here using another M3 screw, about 6 or 8 millimeters or so. But beforehand, I'm going to remove this pigtail because it's easier to do it now, and we're going to use the extension cable. We're not going to need the full meter because, as I said, we're just going to this corner control box. But this has the little special connector that goes into the back of the BL Touch. So at this point, I have the BL Touch raised all the way. That's kind of the state we're going to need it in for a V6 hot end, right about there. And at this point, the tip of the BL Touch in the retracted state is above the nozzle, so it's clearing it. And then when it's extended, it will be touching the bed before the nozzle touches the bed. So that's kind of the ideal scenario. If you have something like a Volcano, the adjustability here should allow you to bring it down far enough that it works with the longer Volcano block, which is kind of in a vertical orientation instead of horizontal like the V6. So feed the extension cable up through the loom here. You kind of have to snake it bit by bit, and eventually we'll come out at the top here. So We also need to feed the DuPont connector through the wire loom so that the connector here that needs to plug into the motor is at this end. And then the BL Touch is going to plug into a control board under here. So we have 3 M3 screws that we have to remove. There's 2 on the top and 1 on the bottom. And now we've exposed the control board. This is where we're going to terminate the BL Touch connection. So the easier of the two is going to be the stepper motor. This DuPont connector here is going to attach to where this cable connects to the board. Be careful, sometimes there's like glue holding it on, and in this case they have little locking tabs that have to be depressed. You may need to get a pair of needle nose pliers or something in there to depress that, to let it let loose. Otherwise, you might pull this entire connector right off the board. It's not the end of the world, they slide back on. So the orientation for this cable, the red wire here, is going to go closest to this old stepper motor that we're not using anymore. So like this, and then just slide it right onto that connector that we unplugged from. You might need to give it a little bit of a wiggle. It should slide right onto those pins. If you were really concerned about it coming loose, you could put a dab of hot glue or something there, but we're gonna have that cover holding all of this additional slack up in there. There's not gonna be any tension on it downward or anything. So this is the connector that we're gonna use for the BL Touch, and the housing on here doesn't leave enough space for us to properly press the connectors onto the pins. So you need to wedge something in here, like a small flathead screwdriver, and very carefully pry it away from the circuit board. In my case, I'm going to use the back side of this X-Acto knife and just gingerly pry it. Using something not sharp would probably be a better idea. And then the BL Touch cable, the DuPont cable, we're going to orient it this way, with brown being closest to the stepper motor on the first 3 pins, like that. So these next 2 pins are going to be black and white, but we have a 3-pin connector on here, so we have to chop off this extra blank pin on the end. You want to be very careful. You don't want to cut the black connector. So let's chop that off. There. So now use a series of zip ties to bundle the extra cable slack we have here together, kind of like I did with the extruder motor cable. Maybe bundle them together like that, and we'll try to hide as much of this as possible under this shroud here. All right, so I got most of it tucked in there, a little bit of this sticking out here, but it looks fine. One thing to be cautious of is that you don't end up pressing any of the wires inside here against the lead screw. If you need to, add some additional zip ties to keep them kind of squished away from there, because they'll wear over time. So now we're ready to turn it around. We will heat it up, as I mentioned. We'll check that the extruder is definitely moving the right direction. I know it is if you followed that wiring scheme I mentioned. But we need to preheat it so that we can do the final hot tightening of the nozzle against the heat break. And we'll also give an extra tighten to the screw in there that is clamping the heater block onto the heater cartridge. Okay, we're going to go to control and temperature, and then crank the nozzle. I think since this is stock firmware, it's probably capped around 250, 260. Okay, that's fine. We'll heat it up to 260, and then we can snug the nozzle tight. So it's not fully up to temperature, but this part doesn't really need to be done super hot. There's already clamping force against the heater cartridge, but just gently give that an extra little tighten, and you should see this gap close slightly. Now that it's up to about 260 degrees, we want to use one wrench to hold the block. You don't want to be pinching any wires or the thermistor or anything. And then use another wrench on the nozzle, and you're just giving it a small amount of force just to snug it up. And then we can lower the temperature back down. So since it's hot, we can actually check, as I had mentioned before, make sure the motion is occurring. If you go to Prepare and Move Axis, and we want to move the extruder, just choose 10 millimeters and move it a little bit. And if you look down in the top, you should actually see the gear move. And at this point, I'll take a small cut piece of PTFE, put it down in there to help guide the filament. I could probably cut that shorter if I wanted. And then fully cool down the machine. And once it's cool, shut it off and we're going to flash the firmware. All right, so you followed the links in the description below to install Visual Studio Code and the Platform IO extension or environment. And then we extracted the Marlin Bug Fix 2.0 to a location of your choosing, and then go File and Open Folder and open that root folder. This is what you'll have. The first thing we want to check is to make sure that we're compiling for the right platform. So if we go to platformio.ini, right here, you want this to be Mega ATmega 2560. So this is an ATmega 2560 Arduino chip that's powering this board. So that's the platform that we want to compile the firmware for. This would be different or potentially different if you're compiling for a different printer, or if you were using a 32-bit board. That's definitely not going to be Arduino Mega. So expand the Marlin folder, and in here we have configuration advanced and configuration.h. As a good starting point, we want to go into this config folder to the examples directory, and we'll grab one from a Creality CR-10S. I don't really care personally about the boot screen and the status screen, so grab these two files, copy them, right-click, copy, and go delete these two, and then paste those ones you just copied here. Okay, I'm not going to delete them because I want to keep these ones, but delete them and paste the ones from the examples folder. And then I'm going to go over all the changes that we're going to make to them. So double click each of these to open them in their own tab. We'll start with configuration.h, and we'll start at the top. Okay, so right at the top, we see who created the config. So this examples config was created by Printed Solid, and the parameters as far as like acceleration and speed and stuff are pretty conservative, but they're a good starting point. I've turned off the custom boot screen and the custom status screen image. If you turn these on, that's where you needed those other files that were in the examples directory. Let's move down further. Okay, I'm going to leave the baud rate at 115,200, and we need to make sure that the board is board ramps Creality. This comes baked into the firmware in that example. I've set the printer name to CR10SV2, super original. And I've just put these little comments beside each of the changes that I've made. And this way, I can refer to any of the lines that I've changed parameters on. So if I just search the rest of the file for that and go to the next location, we'll see what else I've changed. So temp sensor 0. So this is the temperature sensor for the hot end. And we've changed this from a 1 to a 5. As per E3D's documentation, they're using a 104 GT2 GT-2 thermistor, and that's number 5 in this list. So set that like that. The temp sensor bed was 1. I didn't change that. Let's go to the next occurrence. So I've set the maximum temperature for the extruder to 275 from 250. 275 is the highest temperature E3D recommends you running their thermistor at, and the bed max temp is set to 120. Next. Okay, so by default, this is your steps per millimeter for X, Y, Z, and the extruder. The extruder by default would have been 95 with the stock extruder, but as per E3D's documentation, set it to 415 for the Hemera. And then down here, I increased, this is actually not true, get rid of that. I increased the speed max speed for the extruder to 90. You would only ever go that fast maybe on a retract, but I just set it to some ridiculously fast value because it was set to 25. If you end up running something like a volcano or even a super volcano with a large nozzle, you can actually exceed 25. And on a retract, I retract typically around 50 or 60 millimeters a second. It would cap out at 25 because that was the max set there. So I've set that to 90. Okay, classic jerk. So you can use jerk or something called junction deviation. For me, junction deviation doesn't seem to work that great. So I just stick to classic jerk, which is, if you flashed a firmware in the past, it's probably what you're using. It's set to 10 for X and Y, and then Z is set to 0.4. That's fine. All right, so I enable S-curve acceleration. You can leave it off if you'd like, and you can read more about it here. Okay, so probe manually would have been enabled. So it would have been like this, because by default the CR-10S didn't have a probe. Remember, the regular S is where we got this example config from. So I've commented this out like that. And then we've enabled BL Touch. So this would have previously been disabled like that. So I've enabled BL Touch, and now we've set the pin that the BL Touch is using to 19. Okay, so I've added this line in its entirety. It didn't exist there. Okay, down further. So this little graphic kind of explains it better than I can in words. But the nozzle identified by N here and the probe is P. They are, not in the same location. They're offset from each other, and we need to tell it how far offset they are. So based on my measuring and the mount that I'm currently using, the probe is to the left of the nozzle, but only by 3 millimeters. And then it is in front of the nozzle, 50 millimeters. And I've set the Z probe offset to minus 4.2 as an initial starting point. I found that that's about where it is with my mount slid all the way up. But if you were using a different mount, this value would be different. You can also feel free to leave this at 0, because we're going to set this and confirm that value on the printer after we're done flashing anyway. So min probe edge. I don't want to probe any closer to the edge than 30 millimeters. This ensures that I'm missing things like binder clips or anything like that. And it will actually extend the mesh that it builds to the edges of the build plate. Let's go next. All right, so I've enabled the Z min probe repeatability test. So you can issue an M48 and it will use the probe, the BL Touch, repeatedly and tell you like the standard deviation, the min, the max values that it registered, and you can see how repeatable and reliable your probe is. I would definitely recommend doing this, especially if you're using any kind of cloned BL Touch probe, to make sure that it's not wildly inaccurate, or at least not repeatable. Next. Okay, so we need to invert the direction of the extruder stepper motor, that is. So set this to true. And this is because we're using a geared extruder and it just needs to go the other direction. So if you left this at false, when you try to extrude, it's actually going to pull the filament out the top instead of out the nozzle. Let's go next. All right, so this is where we're defining the bed size. Even though it may be listed as a 300 by 300, it's actually closer to 310 by 310. And then here, so this looks a little interesting. When we home the X, the nozzle is actually right off the bed now. It's about 14 millimeters off the bed. So I've accounted for that. The maximum it's allowed to move from its homed position is the width of the bed plus 14 millimeters. So that's why I'm at 324. The Y, it moves 310. It's the max size of the bed. And this menu here, I've enabled this. This allows me to enable or disable the software end stops. So this is where in software, those previous values, it won't let me move X more than 324. If I wanted to, I could remove that protection because I've enabled this menu item. Feel free to not use this if you don't want to. Okay, just make sure that this is set to false. This is for the filament runout sensor. Otherwise, it will be triggering even when there's filament in it. And this line here, so I always recommend leaving this enabled. So by default, when you G28, when you home all the axes, it unloads the bed leveling mesh. So if you did a, probe the bed and then you did a G28, you wouldn't be using that mesh. You wouldn't be compensating for any bed leveling you need to do. This way, anytime you home, it automatically reloads the most previous mesh, most recent mesh. Okay. So I'm setting the mesh inset to 30 millimeters. If I'm just doing mesh bed leveling, so I'm doing a 3x3 grid. Really, you might want to do 4x4 grid. That makes more sense. And this is where I say the home position of the nozzle. When the nozzle is, when the X is homed, when it hits the end stop, we're actually at -14. We're off the bed by 14 millimeters. When we home the Y, we're actually at 0. We're still on the bed. Okay, Z-safe homing. So this will only allow you to home the Z. So in our case, use the probe to sense the bed and figure out what Z equals 0 is. But it will do that in the middle of the bed. In this case, it'll do it at X is 150, Y is 150, which in our case is basically the middle of the bed. This is enabled just to make sure that you're never trying to probe the bed with the probe off the bed. So do it in the center. And here it had the feed rate for X and Y, so how fast X and Y will move when you're homing. It had this set at 20, so that's basically 20 millimeters a second. They times it by 60 because this is actually in millimeters per minute. I increased that to 30, just because I'm impatient. And I've enabled a menu option here that allows me to home X, Y, or Z independently of one another on the LCD screen. Okay, so now we're back at the top. Let's flip over to Configuration Advanced. In Configuration Advanced, let's see where I've made changes. Okay, so we've enabled the high speed mode, if you will, for BL Touch. And I've enabled baby step display total. So this means on the baby step menu, which you can say rapidly press the button in to enable it, which we've got up here, double click for Z baby stepping. It will keep a running total of how much you've modified the baby steps. So if you go in there and you find your first layer is not perfect for whatever reason, and you need it to be a little bit closer, you can use the baby stepping to do that. And then when you exit that menu, if you go back in, you won't know if you've previously made any changes. This will allow you to see that. And you can also use baby steps for the Z probe offset, which we're doing. Okay, linear advance. So I had a bit of an issue here. By default, linear advance does work with 2208s and 2209 trinamic stepper drivers. You just need to enable a couple of their features or they'll shut down. With this particular board, I found that if I have a linear advance enabled at all, the extruder motor will shut itself down in short order, like within the first couple layers if I'm lucky. So I've enabled this, but normally I would have this enabled, not disabled as it is now. And a K factor of 0.06 might be a good starting point. I've changed the load and unload length. So normally if we're using Bowden, we might need to pull out 400 millimeters of filament if we're changing filament, or if the filament runout sensor senses we ran out of filament. In our case, we're direct drive, so I just lowered both of these values there. So because we're running trinamic drivers, we have the options of enabling stealth chop. So Stealth Chop X and Y, that Stealth Chop is the quietest version or quietest method that the Trinamic drivers can be used in. So on X and Y and Z, we're using Stealth Chop. I would never enable Stealth Chop on the extruder. I want to use Spread Cycle. It's, I guess, marginally louder, but it's a higher torque mode for them to be running in. And this would be always set like this, especially if I was using linear advance on a normal machine. And I'm not certain if this makes a difference, but there are different chopper timings, as they're called, for the stepper drivers. And in this case, this would have been set to 12 volts because the CR-10S was 12 volt. I switched it to 24 volt. It just kind of makes sense to use the chopper timings that correspond to the voltage of the system that we're running. So if you're using linear advance with Trinamic drivers, I have always had to enable square wave stepping or they will shut down. Even with this enabled, they were still shutting down on this system. So I'm not using linear advance and I'm just leaving this off. You could probably enable it with no negative effects for sure. All right, and there's one more spot here, Trinamic. So I talked a bunch about these Trinamic drivers. Where did I define them? I defined them back in Configuration Advanced, I believe. Yeah, TMC, there we go. So back here, I didn't actually put comments here, I should have. There we go. So we have to define what stepper drivers we're using on X, Y, Z, the extruder, and Z2, which is actually E1's slot. So we're using 2208s in standalone mode. So as you can see above here, there's a couple different options. The 2208s can run in standalone mode, or they can run in a connected mode, which may be SPI or UART, so you can control them programmatically. In this case, the ones that are built into this board, they're just running as standalone mode. And since they're standalone mode, you change the VREF and the amperage they're running at with the little potentiometer on them. If they were in SPI or UART, you can actually control the amperage via G-code commands, and you can also get their status, and if they're in a temperature overheat kind of situation, you can retrieve that information as well. All right, with that said, I think we're ready to compile this. So if you made changes, just make sure that you save everything. And go to this little alien head thing, Platform IO, and we're going to hit build. All right, success, no error messages. That's always a good sign. So I always do a build before upload, even though upload does a build and then immediately flashes the printer. And you can see that it compiled it for this platform. And so now if we plug in our USB cable and then hit upload, it will flash the printer. All right, now that we flashed it, let's turn this on. We should see the new boot screen. So as I said before, we're using the bug fix version of Marlin 2. Great. So at the bottom, we see the printer name that I put in the configuration and the current temperature of the hot end of the bed. Let's warm everything up. All right, we're just about up to temperature. If we go into configuration, BL Touch, we can just test it and it should click. Great. And then we'll just stow it. And now we'll home all the axes. It should home the Z in the center of the bed. So that was that Z safe homing that we enabled in the firmware. Great. Now we're going to do the probe offset, the probe Z offset. Under configuration, probe Z offset. And so it's set to -4.2. Let's just see if that's correct. To do that, we're going to move the Z down to 0 in small increments. Make sure there's no filament under there. Okay. at this point, that's actually pretty good. If that were off, what we would do, let's pretend that there's lots of a gap in there right now, no drag. We would go to that probe Z offset screen. And then here we would adjust this down further. So more negative would bring the nozzle closer to the bed. So I can demonstrate that. If we go less negative, there's just a huge gap and no drag at all. And as we go further negative, we're bringing the probe down. And as you can see on the screen, it's very, very small increments we're moving it in. So 4.2 seems good. I'm going to turn the filament runout sensor off. We still have it enabled in the firmware, but we've stuck a piece of filament in the filament runout sensor. If we want to actually use it, we're going to have to relocate it maybe somewhere up top so that the filament is feeding down through it. But for now, we're both going to turn it off on the screen and leave filament in it just in case we accidentally turn it back on the unit. And then we want to store these settings. Okay. And now we'll go around and level the corners. Under bed leveling, just do level corners. We're going to go around just a second time. We'll just do this one quickly, just to double check each of the corners. Okay, so now we're completely level. We're just going to go done. So if we home X and Y, we can see that when it's homed, the nozzle is actually to the left of the bed. It's not at 0, 0, which would be this very, very front corner here. So that's why we added that offset on the X when we were configuring the firmware. But from a front to back perspective, it's basically right on the front edge of this, just slightly inset so that it clears these little clips. So as you can see, it's not for the faint of heart. It's very similar to the steps that you would go through with the Titan Arrow if you've watched that video. And the last but not least, in addition to having to relocate the filament runout sensor, maybe up here, to continue to use that, we would have to relocate the spool holder. It makes no sense to have it down here. So a simple option for that is to drill out the holes in the base of the spool holder and get some T-nuts and just attach it here with the spool holder at the front. Or you can print one of the many spool holders that mount to the top rail. Some people I know have a shelf above their printer and they just let the spool go off of a printed spool holder up there. But you'll need to come up with your own solution for your own particular environment. Hopefully you found all of that useful. Remember to like and subscribe, leave a comment down below, let me know if you have a question or if you get stuck on any of these steps and I'll do my best to answer. Thanks for watching.